Oh fuck. Okay. Hey. So in this video I want to cover the model for logistic regression, and the model is 1 over, and let's say y is equal to 1 over 1 plus e to the power or to the exponent of some number. And I'm going to explain how this works, alright? So now let's draw another one where y is equal to e, right? So Euler's number. If you don't know about that, do some research, please. That is Euler's number. So Euler's number, if you don't know anything about it, is basically used for data that has a instantaneous rate of change relative to its size. And what I mean by that, I'm just gonna do a brief cover. So let's say Euler's number. Let's say this is our x and our y, and let's say our graph goes up like that. And let's say this is car speed and this is time. This just means and actually this graph, let me cross this out. Let's just say something like this, right? It could be that or this. Actually, let me just go with this. What this means is Euler's number is usually used when our rate of change, so our derivative, right, or instantaneous rate of change is relative or equal to size. And what I mean by that is if our car speed is equal to, for instance, if our car speed is equal to 500, that means our rate of change of our speed, so how fast our speed is increasing, is also going to be 500. Now this is why Euler's number is one of the fastest functions ever, and it gives us this S-curve because the slope is the same as the size wherever you take it, right? So it's a very fast growing function because again it's well, actually Euler's exponent is one of the fastest growing functions. So Euler's exponent, actually I don't know why I put an X there, exponent. So remember, x relative to rate of change, right? Now how this works, how we're able to get this curve. So let's say e to the exponent of some number, right? It's just gonna grow, and it's gonna let me do z so it's not confusing, and it's gonna eventually start growing slower, right? Obviously. So e like this, and that's the same with any number. So if I do 5 to like x, right? You see it's just gonna grow infinitely. So now if I do 1 plus, and actually let me get rid of this. If I do 1 plus e exponent, right? Now we're gonna grow from 1, right? So we're gonna come here, we're gonna approach 1, and then we're gonna increase, right? And if you're confused about this, it's because say e to the power of like 5 or something, right? We're just adding 1 to that. Like we're adding 1 over and over again, and to 1, and eventually we get to 2, and then we start going up, right? Now, what if I divide 1 divided by Euler's number 2 in exponent, right? So what's gonna happen is we're gonna approach 1, but after we approach 1, you see we're actually decreasing. We're not increasing anymore. And the reason for that is that 1 divided by a number to an exponent is gonna obviously grow negatively. So if I do e to the power of like 5 and I do 1 divided by that number, right, you see it's gonna keep going down and down. And if I do like let's say 75 or also 50, 55, and I do 1 divided by that number, well, it's not gonna show anything, but we're gonna approach 0 pretty much, because it's gonna divide 1 by that number over and over again. It's gonna get smaller, and we're gonna infinitely be at 0. Now if I add 1 to this, remember, we just approach 1 and we start decreasing in this case. And then if I just take the inverse function, if I just take the inverse of this, of our z, it's just gonna flip, giving us this model right here, right? So now our model is between, right, is between 1 and 0. So any predictions is always going to be between 1 and 0, giving us the possibility of making a prediction between 1 and 0. And this is actually the sigmoid function. So that is equal to the sigmoid, right? Very important. This is a sigmoid function, and it's the model we use for logistic regression.